Hello, this is Jake Abbott. In this video, we're going to be talking about bounded input, bounded output stability in reference to continuous time systems, and then in another video, we'll talk about bounded input, bounded output stability of discrete systems. So, up until this point, we've been talking about time response of linear state space equations. And if you look at those time response equations, you can see explicitly whether those time responses decay away to zero, or they grow to infinity, or they're well behaved or not well behaved. You can look explicitly at their properties. But what we'd like to do when we talk about stability is we'd like to say, can we know certain things about how our system will respond without explicitly giving a certain input and then watching how your system's output responds, but just saying, can we sort of know how our system would respond for any input? And that's really the problem of stability. And what it fundamentally comes down to is that stability is the single most important property of systems. Without stability, all your other system properties that you might be interested in, like your time response or your error rejection, your ability to track some desired input signal, all of these things are meaningless unless your system is stable to begin with. Without stability, your system can go completely crazy on you, it can saturate, it can self-destruct, it can hurt somebody. All of the equations that you used to model your system in the first place probably break down. So this stability is going to be this really fundamental property that we analyze before we ever move on to anything else. So at the beginning of this course, we looked at the difference between zero state and zero input response, and that's going to be an important thing here in this stability discussion. So let's sort of review that really quickly. So we're going to consider systems, LTI systems, meaning A, B, C, and D are not varying in time. So we have a system AX plus BU, and then Y of T is equal to C, X of T plus D, U of T. And this is the type of system we're going to be looking at. And we said for a system of this type, if we start this system at some initial condition, x of z equals 0. So every single state is 0 at the beginning. And then u of t is just some arbitrary u of t. It can be whatever we want it to be. If we set both of these things, when you do these things, you will get some y of t. And we call that y of t the zero state response, because it's the y of t that you would get for any u of t if x of z was 0. My initial state was 0. And of course, the u of t you choose affects the y of t. So we're talking about some specific u of t to give you a zero state response. Then we said, if we take our state, we have some x0 that is some arbitrary state. I can have any numbers in this vector, but I set u of t defined as 0 for all time. If I do that, I'll get some other y of t. And that y of t that I get, I'll call that a zero input response. And the cool thing about linear systems we found was that in an arbitrary system, no matter what system you have, I'm going to give it some initial condition that's arbitrary, and I'm going to give it some u that's arbitrary. And what I will get is some y that's arbitrary. The cool thing about linear systems is that the y that you get for this arbitrary x0 and u was the sum of the zero state response and the zero input response. So you can think of these two things separately and then just add them up. And that's a really powerful and cool property of linear systems that we'll take advantage of. So in this video, we're talking about bounded input, bounded output stability. And what we're really talking about is a zero state response in this video. So this is the case we're looking at here. And then we'll handle the other case of the zero input response later. And as you can see from this summation, as long as we handle both cases, then the combined response will be handled by some of these two cases. So we're going to handle this case right here to understand bounded input, bounded output. And we're going to consider this idea that u of t can be anything in general here, but we're going to make sure this is a bounded thing, and we're going to want to see if this is also a bounded thing. We'll talk about that more in a minute. And then in a later video, we'll talk about this other equation and analyze its asymptotic stability or internal stability, or the ways we talk about that. So let's start looking at bounded input, bounded output stability. And we're going to begin by thinking about single input, single output LTI systems. And so if I have a single input, single output system with input U and output Y, the output Y of t is equal to the integral from 0 to time that I'm interested in of g of t minus tau u of tau d tau, and I'll tell you what g is here in a second, which is also equal to an equivalent way of writing it, g of tau times u at t minus tau d tau. And so what is g here? G is our impulse response of our system. So g of t is impulse response. So I have a system that's single input, single output. And the impulse response, if you remember, is if you basically come along and smack that system. You give u this idealized impulse where here is time and here is u of time, and I come along here and I have 0, 0, 0, and then right at time 0, boom, I give it a smack, and then it goes right back to 0. And we call this thing a delta function, delta of t. And that delta function is this idealized thing that goes to infinity at the moment you hit it. So it's infinitely big, but it's also infinitesimally thin. So the area under this curve is equal to 1. So it's infinity high, but it's also 1 over infinity wide. And so the area under that like rectangle is a 1. So this is an impulse. And if I come along and I smack my system will respond to that smack. So if I plot y of t due to that smack, that impulse, so I will see something. I'll observe my system do something. Maybe my system will come along here. And the assumption here is that I have a 0 state response. So at the beginning I'm at 0. So I come along here and I give it a smack and boom, something happens, and then my system responds to that thing. And that response that you get is going to be a function of your system. Different systems will respond differently. So if I give my system this smack, I'll watch its response, and I call this the impulse response, and that is g of t, the impulse response. So it's basically y of t if u of t equals delta t. That is what g of t is. So I have this idea of impulse response, and impulse response is going to be a really important property for stability because basically it's something you can wrap your head around pretty easily. For kind of arbitrarily complicated systems, if you come along and give it a smack and watch its response, you have a single signal that describes its response to that smack. And the cool thing about that is any arbitrary u. So now if I consider some other u of t that's not an impulse, but just some signal that might be our input signal. If you think about it, you can think about any arbitrary signal as sort of a sequence of little smacks. Like I have a smack that's that hard, and then it's immediately followed by a smack that's that hard, and then a smack that's that hard and that hard. And it's like tap, 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 tap. And so I can decompose, and these smacks are infinitesimally close to each other. So I can compose any arbitrary input signal as an infinite summation of little smacks, and the smacks are the value of the signal at that point. And so basically, if I know how my system responds to a smack, and then I can compose any signal as a summation of those smacks, then I can basically understand what y of t will be for any arbitrary u. And this is the integral that solves that problem. So it's basically how you can think about this is, g at tau is some smack that's occurring at tau, and then I'm going to analyze how that smack happened due to some u that happened some time ago. And so I'm gonna have all of these different little u smacks influencing my y, but they have different weights because, as you can see from this signal, a smack that just happens has a big effect on the output, but a smack that happened a long time ago has a small effect on the output. So you have to figure out the way to balance them. And this integral here, which is the convolution integral, is what does that. So we can have any system that's a single input, single output LTI system, and it will have an impulse response, and then y of t is defined through that impulse response. So now we need to talk about what it means for u of t to be bounded. Okay, so this is the topic here. We're looking at bounded u of t. So what does it mean for u of t to be bounded? Well, for u of t to be bounded, we say that the magnitude of u, and we're not going to care if u is positive or negative, it's just how far away it is from 0, basically. So the magnitude of u needs to be less than or equal to some u sub m, and u sub m has to not be infinite. It has to be a real number, and it can be as big as you want. It can be 50 million, it can be 1,000 billion, but it can't be infinity. It has to be a real number. And this has to hold true for all time, greater than or equal to 0. So if there exists some u of m, no matter how big, that you can say that your u is less than or equal to that number for all time, then u is bounded. So there's no sense when you say bounded that it means bounded to be small. It just means bounded. And so, I mean, graphically, you can think about this. If you're plotting u as a function of time, the idea is that there exists these dotted lines somewhere that your signal, while it may be crazy and it may do a lot of things, it'll never leave those bounds. So that's a bounded input. So when we're talking about the definition of what bounded input, bounded output stable means, bounded input, bounded output stable, what we mean is that every bounded input excites a bounded output. So if I say something is bounded input, bounded output stable, that implies that every, and I mean every, bounded input gives me a bounded output. So it's not good enough if you have some arbitrary system and you give it some bounded u, and then you watch y, and y is also bounded. That doesn't prove it's bounded input, bounded output stable. It has to happen for every bounded input. And since you can never experimentally give it every bounded input, or numerically in simulation give it every bounded input, every possible step input, every possible sinusoid, there's no way you could do it. You could never prove something is bounded input, bounded output stable experimentally. Because even if you can disprove it's bounded input, bounded output stable. Because if you give it even a single bounded input and it goes unstable, meaning that y goes unbounded, then you will have proven it is not bounded input, bounded output stable. But you can never experimentally prove that it is because you don't have this ability. So we have to rely on other techniques to prove something is bounded input, bounded output stable. So one thing that has been proven is that a single input, single output system is bibostable if and only if g of t is absolutely integrable. So we say this is absolutely integrable. And the definition of that is that, and remember, g of t is the impulse response of our system, so this is something we can wrap our head around. So if I take my impulse response and I take the magnitude of that impulse response and I integrate that from 0 to time, if that's less than or equal to some number m, which is less than infinity, and it doesn't matter what m is, again, m can be 50 billion if you want, but as long as the integral of this impulse response is less than or equal to some real number that's not infinity, then we say that g of t is absolutely integrable. And it turns out that absolutely integrable g of t is a direct equivalent. So this is an if and only if statement, a synonym with bounded input, bounded output stable. So the cool thing about that, and I mean, think about what we're talking about here. G of t, I give my impulse response to my system. I give it that smack, boom. I watch g of t, and really what I'm doing here is I'm calculating the area under this curve. And as long as the area under this curve doesn't grow to infinity and it has some finite value, then I say that g of t is absolutely integrable, which means that it's bounded input, bounded output stable. And if I already know in advance it's bounded input, bounded output stable, then I know that g of t will be absolutely integrable. And so the nice thing about this is by the definition of bounded input, bounded output stable, we can never prove something is bibostable experimentally. But we can do it by this method, because now we don't have to give it an infinite number of different bounded inputs. We just have to give it one input. the impulse. We give our system an impulse, and of course we do this mathematically because we can't actually give our physical system a signal that has a spike to infinity that's infinitely small. But if we give our system this impulse response, we watch its impulse response, we figure out the area under the curve, and if the area under the curve is a real number, then we know our system is bounded input, bounded output stable. So there's a couple of things that come out of bounded input, bounded output stable systems that are useful to us. So if we know a system in advance, if we know it is bounded input, bounded output stable, so BIBO stable, this implies that as t goes to infinity, so we give our system some sort of input and we're watching as time goes to infinity, there's two kinds of signals that we can look at. One, if we have a signal that's a sinusoid, so let's say u of t is equal to sine of some frequency omega times t, and this is true for all time greater than or equal to 0, so this is the equation, then we know that our output approaches something that looks like g at j omega, this is the magnitude of g at j omega, sine of omega t plus angle of g at j omega, where g of s is the transfer function of our system. So where g of s is the transfer function from u of s to y of s. So basically, anyone who's had a classical controls class, and hopefully you've seen this in other classes besides that, will remember this this idea that if you give sinusoidal signals, then the output is also a sinusoid, but it's phase shifted and it's amplified by the magnitude and phase of g of s, where you evaluate s at j omega. And of j, of course, here is the square root of -1. So this is the imaginary number. So if a system is bounded input, bounded output stable, then this will happen as time goes to infinity. So it may take some time to converge on this sinusoid, but over time it will converge on this sinusoidal response. And then a special case of this sinusoid, which is a sinusoid that's infinitely slow, is just a step input. So if u of t is just equal to some constant a for all time greater than or equal to 0, then my output will go, as time goes to infinity, my output will go to g evaluated at 0 times a. And so we literally take our transfer function, and everywhere there's an s, we substitute a 0, and what we get is some constant, and we call this constant the DC gain of our system. And if we give a bounded input, bounded output stable system a step input of magnitude a, then y over time will converge on a times the DC gain of the system. So we know now how to analyze a system's bounded input, bounded output stability by looking at the absolute integrability of its impulse response. But there's actually a much simpler way to do that, and it's by looking at its poles. So if we have a single input, single output system that has a transfer function that's some numerator polynomial over a denominator polynomial, then, and we're going to assume that this is proper, okay? So that means that the order of the denominator is greater than or equal to the order of the numerator. So this is a proper transfer function. This system is bounded input, bounded output stable, if and only if. So again, this is the two-headed arrow that if I know what's on the left side, I also know what's on the right side. They're direct synonyms. If every pole, and I mean every pole, of g of s is in the open left half plane. So if I were to draw the real axis and the imaginary axis, I'm looking at anything in this open left half plane. And I do not, when I say open left half plane and not closed left half plane, I mean do not include this imaginary axis. If you say the closed left half plane, it means this entire plane and the imaginary axis, but we're only concerned with the open left half plane. So every pole of G of S in open left half plane. And what that really means is that the poles have negative real parts. It doesn't matter what the imaginary part is. There can be no imaginary part, or there can be some positive or negative imaginary part. It doesn't matter as long as the real part is a negative number, and it can't be 0. So we're looking at the poles of a transfer function, but the poles of the transfer function are the same as the roots of d of s equal to 0. Those are equivalent statements. And we use those two terms because they have different meanings. A root is something that has meaning outside of control systems. If I have any polynomial and I set that polynomial equal to 0, the value of s that satisfies the equation is known as a root of that equation. A pole is something that's specific to transfer functions, and that's a value that would make a value of s that would make the denominator polynomial be 0. So they're equivalent statements to each other, but you should use the correct term in the right context. So now we have a really simple way to understand the bounded input, bounded output stability of single input, single output systems. We basically look at the poles and make sure they have negative real parts, and every single one has to have a negative real part. If even a single one has a 0 or a positive real part, it will not be bounded input, bounded output stable. And you can sort of see that in just looking at the raw time response, at least for the positive real parts. With the 0, it's a little more complicated, but you can come up with examples to prove it to yourself relatively easily. So what about multi-input, multi-output transfer functions? We've only been handling single input, single output until now. Well, this is a very simple thing. So for multi-input, multi-output, we have some set of y's, and there's some big matrix of transfer functions, this big matrix G of S, and there's some vector of inputs, and then I have a bunch of little transfer functions that live in here, but 1, 1, G, N, N. So we had previously defined things with the impulse response of single input, single output systems, and so we can also talk about the impulse response of just a single entry. So if I look at the impulse response GII, or IJ I should say, so any of these entries, if I look at that impulse response, each of those impulse responses have to be absolutely integrable. Or I can say if I look at each of these little transfer functions, Gij of S, each of these have to have poles with negative real parts. And for a multi-input, multi-output transfer function to be bounded input, bounded output stable, what we really mean is every individual entry is bounded input, bounded output stable. So if even a single one of these entries is not bounded input, bounded output stable, then we say the entire multi-input, multi-output system is not bounded input, bounded output stable. So basically, one rotten apple spoils the bunch.